Okay, nice. So thank you for the introduction. And yeah, I'm going to start with my presentation. I want to start with the structure of my presentation, the table of contents. So first, I want to give you a short introduction and talk about the motivation. Why are we testing bamboo? Then I want to continue with the material bamboo as well as laminated bamboo lumber, so the engineered bamboo product. And then I'm going to talk about the testing program and continue with the results and discussion. And at the end, I'm going to give a short conclusion and outlook to further work. So let's start with the motivation. Why are we researching on bamboo? Mainly because the climate change is the greatest challenge of the 21st century. So the effects of global warming are already clearly noticeable all around the world. And the need for sustainable solutions in all technical fields is ever increasing and as high as it never was. So bamboo can be a climate-friendly substitute for many non-sustainable materials. When we look at civil engineering, for example, it can be a substitute material for concrete, just as an example. And normally it is, the normal structure is these bamboo culm, and it's further fabricated into laminated bamboo lumber, so that you have a homogeneous material, as you can see in the picture. Yeah, the material, as I already began to talk about, bamboo is a sustainable and renewable material. Furthermore, it is one of the fastest growing plants in the world. So some of the species can grow up to 30 meters in a few weeks. So it is very fast growing. It has a plant structure, a specific plant structure. So it contains of internodal areas, as you can see in the picture on the right. This is the part of the bamboo culm that is hollow. So you have a hollow internodal area. And these hollow areas are separated by the nodes, which are closed and which separate the internodal areas from each other. Furthermore, it is a fibrous material, meaning that there are bamboo fibers running through the culm wall. They're all aligned in the same direction, as you can see in the picture on the right as well. And in the outer part of the culm wall, the fibers, there are more fibers, which results in a harder, which results in the outer part being harder than the inner part. The mechanical properties of the bamboo are comparable or even superior to common wood species, commonly used in many technical applications, for example, civil engineering. Due to the fiber alignment I talked about, there is an anisotropy resulting, so that there's a difference in the material properties according to the direction of the applied load. So and in addition to that, it has a hygroscopicity, meaning that that the material tends to react with the water in the surrounding environment and thereby adjusts its moisture content. There you can see a computer tomography vision of the bamboo wall. So you see all the fibers aligned, and since it is a nodal area, the alignment of the fibers is distracted, and we'll see later on how that affects the material properties of the bamboo. Now to the testing program, we did fatigue testing, cyclic fatigue testing on the machine shown on the left. In addition to that, we did tested different measurement technologies. So we used displacement sensors as well as the DIC camera systems that are shown in the picture. You can see that the specimens were cut out of the material in this bone shape, so that the applied loads didn't have to be that high. And when you see the bird's eye view of the testing, you can see that there were two DIC systems looking at two different surfaces of the specimen. So on the left-hand side, you can see that we were looking at the lamellas and we were hoping to see the reactions in the bamboo material itself. And on the lower side, we are looking at the lamellas, and we wanted to see if there are some material reactions in between the lamellas or in between the bamboo lamellas. Okay, coming to the results, first we did some tensile testing, some basic tensile testing to calculate the average maximum tensile strength, which was nearly 90 megapascal. And according to that tensile strength, we designed our load increase tests that we're following. You can see the result of one of the tests on the left-hand side. You can see that we started our first load level on an upper stress of 20 megapascal. Then we did 10,000 circles per load level, and afterwards we increased the upper stress by 5 megapascal. We were working on a load ratio of 0.1, which means that we stayed in the tensile loading for the entire test. It can be seen that the failure of the specimen was around 60 to 65 megapascal. The material reactions you can see on the maximum strain recorded. You can see that there is a typical stair-shaped ascent of the maximum strain. In the first load levels, you can see that there is not much material reaction, so that there is no significant fracture to the material. When looking at the load levels of 50 or 55 megapascal, you can see that there is a clearly material reaction in the recorded strain and in the calculated dynamic stiffness. Afterwards, we did the load increase tests. We looked for 2 load levels on which we wanted to do some constant amplitude tests. So we choose 35 megapascal, which was a load level where we didn't see a material reaction in the load increase test, and we did the 55 megapascal, which was the load level where we did first see a higher material reaction and a fracture to the material. So first I want to talk about the 35 megapascal. We had a targeted number of cycles of 2 million cycles. We did record the strains by means of the displacement sensors glued to the material, as you can see on the right. As you can see in the diagram on the left, the specimen or the material was capable of reaching the desired 2 million cycles without failure. And afterwards, when you look at the material, there was no damage or no visible damage to the material. We did some hysteresis measurements. So every 30 minutes, we recorded with a frequency of 25 Hertz for 20 seconds. So we recorded 60 cycles and did these hysteresis loops. As you can see, the hysteresis loop is pretty much closed for all the numbers of cycles presented, which leads to the assumption that it was a exclusively elastic material reaction and that there was no real or no plastical damage to the material. When we look at the 55 megapascal load level, the picture is a bit different. So we reached a number of cycles to failure. It was around 185,000 cycles. We did see a stronger material reaction, and the material reaction was the strongest in the nodal area. So I talked about the structure of the bamboo column with the nodes contained. On the pictures, you can see that the nodal area is still clearly visible. And when you look at the DIC recordings, it can be seen that the measured strain was higher in that area, which can be linked to the distraction of the straight alignment of the fibers, and therefore there was a higher strain recorded in the nodal areas. When looking at the hysteresis, once more measured, you can see that the hysteresis loops are clearly open. So just at the first number of cycle, at the first cycle, it was already open, so that there is a that there's a plastical deformation right away, and you can see that the hysteresis loop moved a bit to the right shortly before the failure at 180,000 cycles. Afterwards, we did some more constant amplitude tests on different load levels. As you can see, we tried to calculate or to estimate the first Wöhler curve for the material. It can be seen that in the low cycle fatigue regime, we did a linear fit with the given formula to assumption the Wöhler curve, and in the high cycle fatigue area we used the Pascal equation to estimate the curve. Once more, you can see an overview of the cyclic tests, so the constant amplitude tests, so the different load levels and the reached numbers of cycles to failure. Which was could be seen was that in the high cycle fatigue area, the cracks, or there were cracks in the curves of the bone shape, and the cracks in the testing area preferably started or were located in the nodal areas. So the failure of the specimen once more started in the nodal area. It can be seen when looking at the high cycle fatigue regime. It can be seen that there are again the typical cracks in the curves of the bone, but in the testing area there was a stronger failure according to the higher loads, which means there was a delamination of the individual layers. There were multiple cracks, once again starting at the nodal area of the bamboo, and the crack propagation went into different directions. So the whole bamboo got destroyed. Now I'm coming to the conclusion and outlook. So we were able to prove the general capability of the laminated bamboo lumber material. It has shown an outstanding tensile property. The targeted 2 million cycles could be reached on multiple load levels. The measurement technology used, so the displacement sensors as well as the DIC were able to record occurring material reactions, but there has to be a further improvement of the measurement strategy, or there's a possibility of a further improvement. So maybe of a combination of the displacement sensor and the DIC, or the DIC measuring strategy could be optimized, and and the campaign could be extended, meaning testing on more load levels. And with that, I want to close my presentation. Thank you all for your attention, and I'm ready for any questions.